I want to say a few words. My name is Gabriel Motzkin. I'm the director of the Van Leer Jerusalem Institute, and I regard it as a particular honor to be able to chair this session. First, I want to greet Mark Steiner, in whose honor this is, and say that I participate fully in this event, and congratulations. Now, what I'm going to talk about, because it's my job generally to open conferences, I open something between 3 and 5 a week, and I have to think up something to say about things that I rarely know about. And so I'm not going to talk about mathematics, but I am going to talk about mathematicians. Since I'm the son of a mathematician, and I grew up with one and had him under close observation for over 20 years. And so I had a lot to say about him, and I want to have 4 things to say about mathematicians and 1 thing about Saul Kripke. First of all, mathematicians are lonely people. That has to be understood. They're very lonely people because the people who are closest to them do not understand generally a thing about what they do, and they can't explain it. If you're a physicist,
they can explain it to mathematicians in another field,
but they can't explain it to their wife and kids. And that's the point. They cannot get up. If you're dealing with the inflaton or with Calabi yaw shapes in multidimensional universes, you can explain it. But if you're dealing with pure mathematics, it's very hard to explain, and that gives a tremendous sense of alienation. The second thing that I observed was the geometrical imagination. By that I mean that my father would go around and he'd say, well, do you know what the equation gives the sum of these angles in this room? Or something like that. And all through life, he would go converting the real world into mathematics. And I thought this was a tremendous thing, and it, obviously was a hidden and esoteric teaching of some kind. The third thing is freshness of sensation. Freshness of sensation, so that's something the Romantic poets talked about, but it's true of mathematicians, which is that they are constantly being renewed by what they do, so they don't get, like the rest of us, old and jaded, and they stay in their minds young for a very long time. And the fourth thing is imagination without ambiguity, because mathematics is very much about what is true and what is not true. There are very few situations in pure mathematics that are half true or half false, like in quantum electrodynamics there are, but mathematics, pure mathematics, that rarely happens. So it's imagination without ambiguity. Now, a poor person like me deals with ambiguity without imagination, because I deal all the time in situations where I have to decide things on the basis of 51 to 49%. The one thing I want to say I'm not going to bore you with a long list of Saul Kripke's achievements, whether it's modal logic, the theory of naming, belief. You all know this better than I do. But I want to say one thing that I think is important, which is that Saul Kripke only has an undergraduate degree. And I was moved to find that out, because I think that what we are all about is the life of the mind, the activity of the mind. And when we have these degrees or these ranks, I don't think that's very important. We're seduced by that in the institutions, the medieval institution we live in, which is called a university. But in the end, that's not in the least important. What's really important is the content of what we do and how we pursue that. And so with that, I want to ask Saul Kripke to begin his talk, which, again, it's a great honor to be able to chair. Thank you.
Thank you. Okay, look, I will begin with 2 apologies and also an explanation of why I chose this material. Perhaps I should have begun. I should give the second first. First, this material is, except for perhaps a few remarks that I might throw in, very old and well known to Mark. In fact, did you give, what title did...
The title, I forgot to say. Wittgenstein, Logicism, and Buck-Stopping Identifications of Numbers. That's what we
Now, okay. Now, this title is under the influence of Mark. Originally, where I had buck-stopping identifications of numbers, and then I think it had a subtitle, which just wasn't put in here, a dialogue with Mark Steiner. It was because I did this work under the influence of reading Mark that I thought it was the most appropriate for this conference. On the other hand, the material is mostly, from I might throw in a remark or two, well known to Mark himself. I thought it's not known to most people. This is because, though Mark said some people probably have heard it, so I don't know. I hope that isn't true of too many. I mean, it's another disgusting thing of mine is that I permit big publication lags. I don't know if the stuff was worth publishing at all. It should have been. See, right? Okay. So that's another remark. I also apologize. I have never gotten myself into the universal practice nowadays of using projections and so on. It would be easier to follow my quotes if I instead write something on a whiteboard. The terribleness of my handwriting and the fact that if I have a quote, I have to look it up is another drag. Nevertheless, I meant this as a tribute to Mark. It also was connected to my interest in Wittgenstein, though I don't think of this as his best material, and it isn't his worst one either. But but Mark certainly showed that he appeared to be under some grave misconceptions, right, when he was writing this, and some are a bit surprising. Okay, now, there are three topics. Now, originally this was 2 lectures. I was even praised for this because I set up a problem area or a dichotomy at the end of the first half, and then people were supposed to think about it for a day or two, right? And what I was going to say, and then of course, in this situation, this is lost, but perhaps some things can be therefore compressed. Now, there are 3 problem areas that I wish to deal with, or corresponding to 3 things with the title. The original title was Dere Beliefs about numbers. This was partly under the influence of one of the papers that I'm going to use by Diana Ackerman, who now calls herself something else, but let's call her that, and is about a theory of Dere beliefs about integers. Still, she probably holds the thesis that you have a Dere belief about integers whenever you have what I call a buck stopper in the paper, right? But Mark thought the paper isn't really so much about Dere belief as about when you have a buck stopper, so I am changing it here. I've elsewhere, instead of the term buck stopper, I've heard other people use other things. I've used the term immediately revelatory designator. Okay, all right. Okay, but buck stopper is what I used in this paper. Now, 3 problem areas in this paper. Well, first, I'm not going to deal with the whole program of logicism, but with a certain aspect, namely that the logicists appeared to claim that in order to give an analysis to deal with the notion of number properly, one needed to give some further analysis of what a number is. Right. Now it's somewhat anachronistic to call either Frege or Russell in the usual way that I will. That is, that they thought of the natural numbers as a set of sets in one correspondence, or indeed in a cardinal number in general, right, of which the natural numbers were to be singled out. Frege, of course, viewed natural numbers as extensions of concepts. Russell really thought that sets were simply logical fictions, right, and so on. Right, so neither really fits in. I should mention someone else who gives a similar analysis, little notice. This was a pretty famous mathematician, Heinrich Weber, who did notice that if you think of a natural number in this way, it can't be thought of as some kind of set. I can't remember what term he uses. It might be property or something like that. Indeed. So, well, one problem is, are any set theoretic reductions of natural numbers privileged? Two, are they needed? Right. Okay. Now the logicists naturally thought of the natural numbers and also the infinite cardinal numbers as coming from, we might say, coming from a progress of abstraction, though they wouldn't have put things in this way. 5 must be what is in common to the fingers on this hand, the fingers on this hand, and various other collections of 5 objects. Now, it's the experimental work described in one of the previous talks aside, it certainly is true that we could explain to children what the number 5 is without the idea of an arbitrary natural numbers, by saying, you know, these are 5 objects, these are, and, you know, how you have some other things. It would be a good thing to include, so that some hypotheses, even mentioned by Wittgenstein, that some object may have, in talking about addition, he says, we would say that some object must have disappeared, but some other tribe or something might think otherwise. That one can also do this for, you know, abstract notions, right? 5 seconds have passed, right? There are really 2 basic ideas. One is an ordering, right? Another is simply that of cardinality. Now, one hears tales, in fact, which I think may be true, that without having the idea of natural numbers at all, there are, in general, there are tribes who go 1, 2, 3, 4, 5, and then after a certain small number, many, right? You know, that's all they've learned. Certainly, in principle, this would seem to be possible. So, in that, the logicists are right. Now, what is meant by a process of abstraction here? One might be, and this is the way Cantor seemed to think of it, in terms of even infinite collections and everything, right, that it's something, I was going to compare it to a sort of Platonic format. An infinite, a cardinal is a collection of abstract units, right, of which all we can say about this is that they are different, right? Now, but how do we get such a notion? Well, we take an ordinary collection and then forget about every property except that the things are different. Now, something I've only had to read hastily, doesn't like my throwing in Frege here, but anyway, I thought that among critics of this type of idea are Berkeley and Frege. Look, just because you've forgotten about something doesn't mean that it isn't so. So, can we really form ideas by forgetting things? We really do remember them, maybe, right? So, at any rate, another idea is this, that we identify objects. I mean, this is, of course, the way things are done in mathematics, forming quotient spaces, topological spaces, homomorphic images of algebraic structures, rings, groups, and so on, right? We have an equivalence relation and then take the abstract object corresponding to the thing to be the things identified under the equivalence relation. Now, there are two problems with reconciling this with ordinary set theory. One thing often remarked is that the classes involved are too large, right? The other is that one of the basic set theory notions, and this, Russell wasn't thinking in terms of what we would call contemporary set theory, but one notion is violated where you have n things. An equation can have, say, n roots, one of which might be n itself, right? Then on this idea, one set would be a member, two sets would be members of each other, which contradicts the basic axioms, not only of Russellian type theory, but of contemporary set theory. Now, there are various proposals that might form a way out of this, and certainly some people, nowadays, category theorists speak in a way that might appear to violate such a principle. But we are thinking here where A cannot be a member of V and V of A, right? But we are thinking in terms of traditional set theoretic ideas in which everything is built from the ground up. I will also say that there are arguments, and this is mentioned by Weber, who says, when he takes a cardinal number, he doesn't mean a set of a certain type, but I don't know what term he uses. I think it might be property. I don't know whether it corresponds to nowadays to what might be proper class C, but at any rate, we do not think of this as one of the sets itself, and so on. And there are indeed reasons which, if I have time, in terms of intentional logic, where one might really, if one followed out this idea, want the Frege-Russell numbers to much as they can be defended at all to be properties in any case, rather than extensions or even proper classes at all. Now, so, having said this in motivation for the logicist set of ideas, I should now say that Russell emphasizes very strongly that the notion of natural number cannot be taken as primitive. His main criticism of Hilbert, ignoring the rest of the entire Hilbert program, is that Hilbert was content to do so. And the idea was, well, any progression might fit this condition. A progression, is just anything the form, starting with an initial element and then some successor operation, and speaking circularly, applying it an arbitrary number of times, or, there's the set theoretic definition given by Frege and Dedekind as the intersection of all things closed in successor, right? If you have the notion of a well-ordering, it could be a well-ordering, the smallest well-ordering without a last element, but every proper initial segment has a last element. So this is another idea. Now, Russell says simply, look, of course we need some sort of analysis of what a natural number is, because if we didn't, the numbers falling after 536, say, would form a progression also. You could cut off any initial segment, right? And to say it would be to say that there are as some at least character of the Zoroastrians, I've heard that there are two gods in the universe who would mean in this that there are 537. Say, but that is impossible, right? And, analogous mistakes could be made again and again. Now, originally when I gave these lectures, I did not think there was much acceptance of Russell's idea. Quine says, any progression can be fitted to the condition that there be a proper way of explaining what's meant to say there are n elements, namely that the elements from the first to the nth are in one-to-one correspondence, right? with these elements. Now, actually, Paul Ben-Asraf gave a somewhat better answer to this. Michael Dummett actually defends, to a degree, the Russellian objection. I mean, that is, Husserl, according to him, thought the numbers began with 2. Some might think they begin with 0. Who is to say? See, right? And nothing is given in terms of the structure, right? Now, Ben-Asraf, and he also thinks he's refuting Ben-Asraf, but if I understand Ben-Asraf's paper, what numbers could not be, which defends the idea that any progression will do. Actually, it doesn't defend it. It puts some extra conditions later retracted. But it certainly, if you take the familiar numbers used in contemporary set theory to represent the natural numbers, such as here, this is the empty set. Then Gemello thought the empty set represented 0. This represents 1. The unit set operation is a successor operation. Right? The von Neumann numbers actually anticipated in unpublished writings by Gemello himself, as he mentions it, though the von Neumann, but also by Miramanov, I believe, in print. Are the same type of thing, only every number is identified. There's the empty set, then indeed the set containing the empty set, but then this is different. Every number, to put things circularly, is identified with the things that come before it, right? We can put it that way. So they gradually increase in length. This makes the less than relation, first it naturally extends to the ordinals, and second, it makes the less than relation rather than the successor relation identified with the epsilon relation. Okay, and the point of Ben-Asraf's paper is if you had two people calculating with these two different definitions of numbers, right, no one, unless they told you, could tell you which one they were using, right? So numbers could be identified with the science of arbitrary progressions, right? Actually, Ben-Asraf places the requirement that the progression must be recursive. He later retracted. As stated, the requirement is difficult to defend. I mean, he takes the natural numbers, then he imagines some non-effective scrambling of them and says, so could these be the natural numbers too, even though they have the same order type? But that doesn't work because because we won't be able to tell whether one number is less than another. In fact, we won't be able to tell what the successor is, and we should place a requirement. But this is all relative. If you thought of the first thing as the natural numbers, the second thing, rather, is the natural numbers, the scrambled version, then the first thing would be scrambled, right? So as stated, Ben-Asraf's extra requirement couldn't be defended. Now, I actually don't remember Ben-Asraf's retraction so much as to whether it is an explicit recognition at this point, but probably it is. Nevertheless, not everything I say will be maintained absolutely later on. That's the way the talks went, and in the present case, something can be said for what Van Ashraf is requiring in special cases. I will say something about that later on. There might be, if interest, as I say, one might, if one wanted to defend the Frege-Russell notion at all, require some things to be a property, and there might be some other restrictions on what progressions are allowed for similar reasons. These have to do more with modality and intentionality than with the purely set theoretic thing as we are talking about it. By the way, in spite of some appearances in which some things will appear to mirror various notions that some people might regard as nominalist, I'm not concerned with this issue at all, and will just assume the reality of mathematical objects, and if someone wants to look at things another way, I'm just talking about ordinary mathematical discourse. All right, now, so look, as I say, Dummett, I thought that it was universally agreed that Quine was right and Dummett and Russell wrong, but Dummett does defend Russell on this issue, and I'm not sure exactly what conclusion he wishes to draw. He says this isn't to show that some conception of natural numbers must be privileged or something like that. So, however, he includes Ben Ashraf's number paper as one of the things he attacked, but actually Ben Ashraf explicitly says that not only the progression itself, but the explanation of how it's used in counting is part of the conception of natural number given by any progression, right? That will say, presumably, and counting means two things. First, of course, you count in order by successive, but then he also talks about transitive counting, counting other objects like these, or two objects on the table. So, then you must say which number counts as 0 or 1 or whatever, and the normal way of counting would be from the number 1 to n. We could, of course, artificially, since many people begin with a 0, count simply from the empty set. Then you would be counting up through n minus 1. Okay. Now, having said this, I think there is no reason to think that Ben Ashraf is wrong. Ben Ashraf makes a suggestion at the end of his paper that which also seems to be suggested in a way in the opening paragraphs of Wittgenstein's philosophical investigations. Wittgenstein does not go into this. Maybe really all you have is not a system of objects called numbers, but of the numerals themselves, right? Which one thinks of if they're used in counting as if they were designating a type of object. You know, Wittgenstein actually may be drawing a moral from this, that the relation is not the same as Fido to Fido or Mark Steiner to Mark Steiner. Though we may say that the numeral designates its numbers, we're saying something about how it is used. However, if this is indeed an infinite sequence of objects, right? You know, just as in, say, many analyses, I mean, Gödel showed how the other way around the expressions of language could correspond to numbers, right? Or Cantor showed this. Even in a way, people before came close to showing this, right? And Chomsky emphasizes the infinity of the expressions of natural language. It would be true that if we did have infinitely many numerals, no advance would really be made, or not much of an advance. We'd have some particular progression which would have to be explained. What? By abstraction of some kind from, from sound shapes and so on. I'm not thinking here, say, of like the Quine-Goodman paper or something like that doubts that there are infinitely many such things that you're not in these papers, and I would be getting a field to do so. Now, as I say, we've gotten away from the Frege-Russell conception if we allow arbitrary progressions. We also must say there's something to the Frege-Russell idea, because it is not going to be the case that natural numbers, it is not going to be the case that natural numbers are identified with these equivalence classes, and each one could be thought of, so to speak, by itself. It is obviously impossible for us to conceive of it that way, let alone say what we can do with the infinite cardinals, right? It is obviously difficult for us to conceive of an infinite, of a large, finite collection, the way we can think of three things. I think Mark, in a very recent piece of writing, only got a glance at mentioned some rabbi who supposedly could do this. But there is also a case of some idiot savants reported by Gerald Sachs, who not Gerald Sachs, Oliver Sachs, who when a set of matches is thrown on the floor, can say at a glance how many there are. It's not so big, but none of us could do this, right? It is okay. Now, let me get to the main point, which is a reaction to Mark Steiner's criticism of Wittgenstein. The work in question of Wittgenstein comes from the remarks on the foundations of mathematics, and one trouble I have is that Mark's copy quotes it from part 2. In the newer edition, it would change to part 3, which is what I actually have, right? Now, Wittgenstein appears to believe the following, right? He is actually directing everything towards Principia Mathematica, right? But what he says, if it were right, would probably apply also to contemporary, say, Zermelo or ZF set theory too. And I don't think of it as among his best thinking, because as Mark readily shows, there are some big misconceptions in it. There are some big misconceptions in it. Now, Wittgenstein thinks something like the following. He thinks that in Principia, I tried to write it down, but I think I might. Yeah. One could not do ordinary decimal calculation as we normally do it. It would be impossible, for example, to multiply 234 by 537 is one example, which he actually puts in the mouth of someone defending Principia. He says, well, of course one cannot do this in the ordinary sense, or presumably add these numbers. Nevertheless, isn't there a calculation corresponding to this in Principia? And he thinks the corresponding calculation must be something like what some people have called one given in stroke notation. That is, you have a 0 and a successor operation, and the number n is identified simply with n iterates of the successor operation, or it could be identified with n simple strokes. So he doesn't put things that way, right? If you wanted 0, it could be the empty sequence of strokes, so I don't know if he himself would like that. Now, he assumes that we cannot develop this in Principia. In the discussion class where Turing was present, and notes have been taken by Cora Diamond. Now, of course, there are limitations to these notes because they're just based on lecture notes of students and might have some unreliabilities in this, but this seems quite consistent, right? This seems quite consistent with what Wittgenstein is saying. This seems quite consistent with what Wittgenstein is saying. Turing says, well, look, couldn't you find a corresponding calculation to this in Principia Mathematica? And Wittgenstein replies, yes, but it is a bit of mathematics. That is presumably a meta-mathematical informal argument to show that the calculations correspond. Now, I will say some people even thought it was, or one person who spoke to me anyway, thought it was an objection to Marx that he took an argument like this seriously. Look, Wittgenstein's premises are, first, that a proof to be taken in cannot be impossibly long to comprehend. And you can't comprehend it just step by step and so on. Now, things might be said about this because in mathematics nowadays we do have proofs for which the problem of whether they really can be taken in, some were done by groups of people who handled only parts and so on, right? Whether they can really be taken in is a problem, but I think we will agree that it would be a strong objection to Principia Mathematica or contemporary set theory if elementary computations could not be carried out in it without leading to incomprehensibly long proofs, and in particular, if we could not develop ordinary decimal notation and so on in the system. Now, it is very strange that Wittgenstein even thought this the case. I don't, in that way, I don't see this as some of his best work because, of course, the invention of the decimal was a mathematical discovery, and if other mathematical discoveries are supposed to be carried out in set theory, surely this one should have been also, right? But he does not consider this. He also sometimes seems to think that in Wittgenstein, for example, addition must be defined in terms of what some people have called first-order logicism. To make things short, I will not write things on the board. He uses an expression, tautology. What he means by this covers quantification theory and at least things that are obviously valid, right? So, of course, to say that 223 plus 57 is something or other is true if and only if some statement about two disjoint predicates F and G, right? One says that there exist some 37 things and another such that there are 53 things, distinct, satisfying if they are disjoint. I won't write this all out, right? Then the union, there must be the sum of these, right? And so on, right? Corresponding to it. And of course, he is right that we believe that such things are valid because we know how to do numerical calculation, not the other way round, right? And sometimes he talks as if this is Russell's theory. Now, of course, it isn't Russell's theory because Russell gives explicit definitions of cardinals, right? Forgetting the logical fictions aspect of some of this, where he really has an intentional theory for which he on which he bases things, right? And he does not hold that a sum is simply such a first-order sum. Now, one might defend Wittgenstein in part on this if one thinks that if one were given the basic Russellian definitions, if you think what will be true for a certain sum to come out, this will be true if and only if such a first-order thing is valid, right? And in that sense, it reduces to that. And he will be right that there ought to be some other way of knowing this other than by some direct proof of the validity of this first-order thing. So much of this is correct, and I think Mark says this could be an objection to first-order logicism. It also, however, that is, such arithmetical statements as being reduced to the validity of various first-order things. But second, one might say that given Russell's definitions, it will turn out that this is true if and only if such a first-order thing is valid, and this is something we're only going to know in another way, right? Okay, so this much is true, but of course it is not true. It is not true that decimal calculation cannot be carried out in Principia. And as Mark rightly says in his book, of a theorem given in decimal notation, if we translated decimal notation into Pascalian equivalent, the theorem supposedly would have to be written out with large number of strokes, as I said, and then the Russellian definition of plus, and then equals. Then, well, this would be something that would be of little help to what we actually do, right? But what Mark says, and this is all correct, the decimal system, like the stroke notation or the Principia notation, is simply first let me start here. The decimal system is in and itself not a method of calculation, though it certainly lends itself to a certain technique of calculation. Decimal system, like the stroke notation or the Principia notation, is simply a method for generating numerals. One can grasp the method without knowing yet how to calculate. The advantage of the decimal system of every system that has a base is that each numeral has a dual meaning, provably equivalent. On the other hand, each non-zero numeral designates the successor of some other number whose numeral can be obtained in a simple mechanical way. Thus, the numeral 1, 1 denotes the successor of 10 and does correspond to 11 successor symbols followed by 0 in set theory. But on the other hand, each numeral is also a polynomial in 10. E.g., 533 is short for 5 times 10 squared plus 3 times, well, 5, 3 times, he just says 10 theoretically to make this all uniform. It would be this, right. Or 533 plus 3 times, okay. These unnecessary powers are omitted, right, in Mark's presentation, right. Now, we can switch back and forth from one meaning of decimal system numerals to the other as occasion arises. We can prove that each number is representable by a polynomial of 10, and that each polynomial of 10 yields a number. Once we have polynomial representations of numbers, we can use many shortcuts based upon the distributive, commutative, and associative laws. Any decimal number, right, can be represented as a sum of powers of 10 with some coefficients, right? And this will be a general thing, or that a special case of things in polynomial rings and so on. But here, just in the case of the cardinal numbers. Okay, so we can prove in Principia, or in contemporary set theory, we can prove in Principia using these terms, all necessary additions, multiplications, and so on, using the associative and distributive and so on laws. I don't know now. Look, Wittgenstein also seems to imagine something that some unnamed logicians may think that, for example, exponentiation, just 17 to the n, is just something short for 17 times 17 times 17 times 17 written n times, right? And of course, in fact, right, in set theory we can define the nth iterate of an arbitrary operation, right, and get from addition to multiplication and from multiplication to exponentiation by having given such a definition. It was the special achievement of Gödel to show that even in first order logic, if you have plus and times, you can get exponentiation, but by explicit definition, not as some sort of just seeing another aspect, or whatever Wittgenstein calls it, right, of this thing written on the board. I must say, this is a side remark, Jonathan, I mean, making all this is true, but I do think in school the teacher will explain it to us in this way, right? That Wittgenstein is imagining and say, so you see, we call this, we call this an exponent and so on, right? We call repeated addition, multiplication, and so on, and we count the number of times, right? Representing this directly in logic would somehow, and is not really quite captured by these conventional devices, I think. So, or sometimes I feel that. So I think sometimes something is missing here. But anyway, a statement that this is impossible, or that it's simply 17 to the 10th is just short for 17 times, 17 so many times, and logicians think that is simply, of course, a mistake. Nevertheless, there may be something more to say about this, and I don't know quite what it is. Okay, now, even though when we understand these things, we of course understand the definitions in question, right? Okay, then one can prove the conventional laws, right, needed to perform the arithmetic operations on numbers in decimal notation. Gosh, somehow this is as long as it ever was, yet I thought I would be able to condense it. The second half can be a bit shorter. I add in remarks. Now, what is missing in this? Originally, I put Dirac beliefs about numbers in the title. This was under the influence of a paper by Diana Ackerman, as I say, who calls it Dirac proposition latitudes towards integers. She discusses, but the main point is given really in this. Mark rightly says that there are two meanings to decimal notation. Someone in elementary school might learn how to generate the decimal numbers, right? Just by giving school rules for generating them, right? Just by giving school rules for generating them, they may know nothing of addition, multiplication, of exponentiation yet, though eventually, no doubt, they are intended to learn this, right? That's why Mark says there are two meanings provably equivalent. But in his entire discussion, there is nothing really about the first meaning, right? And the second meaning, in which they are sums of powers of 10 with some coefficients and so on, right? Well, yes, but it naturally makes it look as if the following question is relevant. Yes, okay, you have said how to determine such a number, right? But which number is that one? Now, that is, you've determined it in terms of various operations, but then carry out the calculation. Which number is it? And then you seem to be back to square one, unless you have done something else, right? You are back to the Principia impossibly long number again. See, right? So, so what is, I think, the lacuna in Mark's discussion of this is an explanation of the second meaning, right? There also might be as I will say now, some question of the role of decimals in our lives, our culture. Well, I will go directly into that. Now, the paper by Diana Ackerman that I am talking about is called Dirac propositional attitudes toward integers. But if it were put in terms of what propositional attitudes are towards direct representations of the integers, where you do not have to ask, as you do, no matter how simple the thing may be, such as, say, the square root of 64 or something, right? But what integer is that, right? Where you don't have to ask that, I call a buck stopper. The connection of that with Dirac attitudes and so on might be controversial. Okay, right. I largely, well, I am not inclined to everything she says to accept here, but I am probably largely inclined to accept something of what she says about the connection. But she discusses various theories, anyway, of when we have a Dirac propositional attitude towards an integer. I actually have a paper on the notion of Dirac and so on, and of people who argue, unless you want me to argue against such people, or people who argue that it shouldn't be a serious science anyway, even if it's in popular discourse, or that any exportation goes. We all believe of this, no matter how much it is described of the subject, right, and so on, right. Nor do such notions as knowing who and knowing which make sense. There can be questions about this, but I will leave them out. I will say that if one thought that these were justified in elementary discourse, but under the influence of Cohn, thought that we shouldn't have any proletarian ways of designating a number, like f of n. Well, one man philosopher said he thinks, like, there's someone I believe to be a spy. That's, standard examples because of Klein's thing. Those never occur in a serious science, nor does knowing which or knowing of a number. It seems to me that certainly ordinary recursion theory or computability is a serious science. If all ways of designating a number were on a par, what would be the point of this? I mean, a function f is computable when given n, and here we can just identify it with stroke notation if we like, right? We can tell what f of n is, right? But why isn't the answer simply that? Every function is computable. I mean, that is, or it's all relative, so it depends on the way you think of it. We know what the answer is. It's f of n, right? Of course, I mean, we may not know how many planets there are, but the number of planets, in fact, Klein's standard example on this is generally believed to be wrong nowadays, I guess. But we assume that it is right. Or it could be an arithmetical, more now, even if a function is computable, if it requires computation, we don't really know directly what it is. Now, Ackerman's view is the following. I suggest the following positive view of Dirac propositional attitudes towards non-negative integers. Or one might call this directly representing positive integers. Or non-negative integers. She includes 0. I will argue below, I suggest that N is such that N believes it Dirac to be F, if and only if he believes at least one member of A. Dictionary definitions of the term numeral seem surprisingly unspecific. Webster's New World dictionary is quoted, right? But does 8 plus 3 express a number? Does the smallest perfect number? To avoid misunderstanding, I stipulate that count as numerals single Arabic, Roman, etc. numerals such as 5 and V, and strings of them such as 5, 2, 3, or X, double I, for 12, right? She also obviously counts strings of the ordinary Arabic numerals. In fact, she says that, right? Hindu Arabic numerals, they really, I suppose, should be called. Such as 523, her example, 523. But not such mathematical expressions as 5 plus 8, 10 cubed, minus 2, 9 over 3, or square root of 64. Let alone descriptions, actually she says or, descriptions such as the smallest perfect number. Then she says her account is immune to objections she made for other people's view of Dirac, some of which are far too general, and it seems to accord with most of our intuitions, or most of my central intuitions about a non-negative integer, if such is believed by Dirac by someone to have a property. Now, what is special, what is expressed by numerals as compared with other standard names? I cannot answer this precisely, but there seems to be a sense in which a numeral directly specifies the position of its referent. Of course, a standard name that is a mathematical description, such as the smallest perfect number, also specifies the position of its reference. But this position cannot be known directly simply by understanding the numeral without having any mathematical knowledge beyond what is necessary to understand the numeral. I do not mean to suggest that one can understand 75 without having the concept of any other numbers. 75 can be only understood in the context of a simple system of numerals. Okay. And what is it to understand, know and understand a symbol of numerals? It is to be able to generate in order the progression of the numerals, right? And knowing how to count transitively. This is Benasref's term, I think, really, though she doesn't mention him, how to count marbles in accord with the progression, right? So 1, 2, 3, 4, 5. I mentioned this already. Now, actually, once one knows what in the numerals 1 is, right, and how to count in the intransitive sense from 1, then the explanation of how to count transitively is uniform. So it is really the first requirement that is needed. Now, she says, however, the following. Okay. you know, I'm going to put it a little differently from her, and she actually may be most worried by a problem that I am simply going to ignore. It may sometimes arise, but rarely. I mean, different groups of people, different cultures may use different systems, like the Roman system of the decimal system, another base 12, right? Whatever, right? Now, in all these cases, I will say, we know these systems of numerals well enough to be able to generate them as a progression, and therefore, in principle, also to count transitively, right? Suppose one, for example, had a system with the base 25, that could most easily be generated by the letters of the alphabet from A through Y, standing for the numbers Z. I leave out as more naturally standing for 0. Okay, right? Okay. So, now, I have a strong feeling that, I mean, other examples could be given, but I am taking too long. But this will be one. According to her criterion, I mean, if I have any system of numerals that I have mastered to the extent that I could do this, and we could have a system to the base 25, right, using letters of the alphabet like this, right? Wittgenstein actually mentions letters of the alphabet in the beginning of philosophical investigation. So, I think, I don't know what 25 to the 4th is without a calculation, right? But, of course, to this base, it's pretty easy to see what it is. Y followed by 4 zeros, right? Many other calculations, 543 times 237 or whatever, right, could be made to appear to be easy given this criterion, right? Now, she says she doesn't want a stronger criterion, say one that we regard the decimal system as privilege, so that only numerals in that system can be exported. That is, we can get a Dere belief about them. Whether you identify this with Dere belief is not too important. This is preposterous and would invite the tiresomely trendy charge of ethnocentrism. Well, even though she thinks it's tiresomely trendy, I think she thinks that it's right. There are all kinds of analogs to this. Just in this country, when a price is quoted to me in shekels, I think, so what is that? And have to try to figure out what it might be in dollars because of the way I was trained. Right? Now, what is going on here? Is, say, just in a numerical case, is this just an illusion? Or is there really some objective fact that I don't know this? Now, there are two possibilities. Scylla and Charybdis, taking Charybdis, that would be what she calls the silly view that our culture is the privileged one, right? That can't be right, right? On the other hand, Scylla would be the idea that, and this appeals to more people, that there's nothing to the sense that I don't know what number this is when it's easily calculable in another base that I am not trained in, but understand well enough to know how it is generated and so on, right? There's nothing to this. Of course, I don't know how this is expressed in decimal, sorry, but that's another question. In the same way, I don't know how my decimal number might be expressed in one of these other notations, right? So, that appeals to many more people. Now, the reason I've made this into 2 lectures, and if even been praised for doing so, is that I give some people to think what to say about this. Some people are inclined to Scylla, I think very few, to Charybdis. There are 2 problems that remain here. First, what should we say about the dilemma in question, A, right? And B, in Marx' discussion of the natural numbers, though he says that there are 2 views that are provably equivalent, he gives no account in conventional set theory or Principia type theory of the other meaning of the decimal system, in which it is numerals, right, and not simply polynomial expressions. And such an account ought to be given. So these are the 2 problems. Now, I hope second lecture can be shorter, second half of this can be shorter with 2 lectures.
Do you want a break, or do you want to just go to a question period? Or do you want to do a second lecture still?
Oh, I want to do a second lecture because I haven't solved the problem, right?
All right.
I mean, now, do you want a break? You want me to go on and be very long? Right, I mean, you have no particular... unless people want to break it with a question or 2, but I will really give my answers or something, or my views on some of these things in the second half. Yeah? 1?
2 minutes, okay. So we're going to take a very short break, and most of you are not liberated, and come back for the second lecture.
Yeah, Carl.
Okay, everybody, I think that we should continue.
Mark himself will know.
I think we should continue now. And how long do you think your second lecture will be? 40 minutes, 30 minutes? You don't know.
I don't know.
You know, good.
But I don't think it will be as long. But you're right. I shouldn't have let myself lose my audience or anything. So.
No, that was obvious because it's dinner time. So that there we go. All right, everybody, we're going to, with your all dedicated mathematicians, we now go to part 2 of the lecture. Please, Saul.
Okay. Look. In talking about Debray belief, and I presume you would apply this to the considerations in Ackerman's paper too. Dennett holds that any term is equally exportable. I mean the Quinian sort of view. The Quinian sort of view. First, he says that, for example, if J. Edgar Hoover knows that some unique person committed the murder, then there is someone he believes committed the murder, right? And presumably, if you put it in terms of what is a buckstopper, you would make the same remark, unless we have a principled criterion, right, for differentiating one way of referring to the object to another. We can't make any relevant distinctions here. Now, I don't believe him in general. That is, people use complex criteria for things, and a principal distinction means the one that Dennett can think of after a little while, right? But to me, this is a little too quick, because I think these things are too hard. Nevertheless, in the present instance, I think something can indeed be said about what a conception of the natural numbers and so on might be. Okay, look, and this is, I don't know quite how to define this, but a preferred representation should be structurally revelatory. Now, what do I mean by this? For example, consider the hereditarily finite sets. You have, this is the empty set. And then there's singleton, the empty set, and there is the set of these two, in which these could be written in the opposite order, of course, and it will be the same set, right? Okay, and so on, right? Okay? Now, now one could observe there might be other notations for the hereditarily finite sets that simply scramble, right? These, you might say, let this represent the empty set, and or this, or reverse what these two represent, and so on, right? But there is obviously something inferior about these notations. It's not quite an isomorphism, since we don't have a convention, right? How to represent distinct sets you know, they're the same regardless of the order in which their members are listed, right? But various notations for the hereditarily finite sets are not to be preferred, right? Okay, now, in this sense, there's something to Ben-Ashereff's claim, and then later withdrawn, right, that a proper progression for the natural numbers must be recursive, because if in a structurally revelatory notation, right, the natural numbers were identified with something such that you could not compute, right, the representation, the ordering relation, or the representation of successor in the hereditarily finite sets, as opposed to the Zermelo numbers and the von Neumann numbers, where you can do this, there would be something unusable about this notation, right? So it's not as if this had nothing to it after all. But what I am trying to claim is that things can be read backwards from this. We should assume that our notations for the natural numbers are structurally revelatory. In particular, I was asking first, how do we represent in set theory the other meaning Mark mentioned, right, for the numerals in which they don't appear to be polynomial expressions? We then can prove within set theory that they are equivalent, right? Now, if it's the decimal system, we can have any any 10 objects. Or maybe I need to generate 8, 9, any 10 objects, right, which I just call this, right, and the appropriate representation of decimal notation will be these numbers in which we don't allow a zero at the beginning. Right. I will say or if we do allow it, we count it as just the same as if the zero were not in the beginning. Right. Otherwise, it can be anywhere in the middle, right? And we have finite sequence of these lexicographically ordered. That is, I mean, this is the order of the, this is the ordering of the objects, right? And a lexicographic ordering is like an ordering in a dictionary, right? Anything beginning with an A precedes anything beginning with a B, as long as they're the same length. Lexicographic ordered if they have the same length. A longer sequence always comes after a shorter one. Remember where the Z does not count, as in the beginning. Now, actually, these restrictions, gosh, since I seem to have taken so long, they suggest a more natural system, which also could be called decimal. And I don't know, the first hint of it I see is in the book by Raymond Smulyan, in which we don't have this funny restriction that it can't begin with one of the terms. Okay, right. It also could be a decimal system, only 10 is represented by one digit. Now, I guess that's all I'm going to be able to say about that. All right, now, finite sequences of these form a progression so ordered, right? And my assumption is to read backwards. That is, someone who uses a given system thinks of the numbers in a way such that the notation will be structurally revelatory. I have defined this in set theory. I haven't worried what the entities here are, right? So it could be any such bunch of entities ordered in a certain order. I later make an argument that we should try to get as close to the Frege-Russell's numbers as we can. Now, there's a problem, of course, there are problems with these numbers, but let me leave that out because I've been taking so long. Now, and I might be asked, what do I mean by a finite sequence of these? The notion of finiteness might involve that of natural number itself, but okay, a finite linear ordering of distinct objects is easy enough to define. Remember, I defined the idea of a progression of natural numbers is that every proper initial segment is not only well-ordered, but converse well-ordered, right? Here, as long as the entities involved are distinct, a finite linear ordering is one in which they're well-ordered and their converse is well-ordered. Or perhaps what one might say is, in other words, that everything has a first and a greatest. Every subset has a first and a last element, right? Okay, right. Now, since in these things repetitions are allowed in the sequence, it really has to be such an ordering indexed on, or, put into one-to-one correspondence with ordered pairs, right, of such a distinct a sequence where every object is distinct. Okay, so I don't need, though sometimes I thought one could use just as a base for the sum preferred notion of natural number and then define finiteness that way. And then get an ordinary system from that. That's another way of looking at things. But it's nicer to give a definition of finiteness by itself. And this definition is to be found in the literature, I think, as I found it, goes back, I think, maybe to Termelo or someone. There are other definitions of finiteness used to be a topic in that there papers were written on it. There's one survey by Tarski of many such definitions. See, right. There's Dedekind's famous definition, right? Of course, is the first. Okay, now, but that depends on the axiom of choice, right? Okay, and also I want the idea of finite ordered strings rather than just finite sets of these, right? Okay, so, these form a progression, and my suggestion is, first, that what I've carried out is an appropriate definition of set theory. The other thing Mark wanted that could be provably equivalent then to the polynomial representation, but is a numeral, right, in the sense that Mark actually mentions, right, and that Diane Ackerman wants, right. It, in some sense, designates the natural number directly. Okay. Second, I suggest that, and there will be some reservations about this, which I could actually, maybe I should leave it for discussion. When we are brought up this way, we are brought up in school to think of the natural numbers in this way, right? That is, that they are such finite sequences. Usually one will be told in school something, probably not explicitly in terms of powers, but this space represents the ones, this the tens, this the hundreds, right? And actually, something like that is in our elementary training of the natural numbers too, right? But it need not have been. And I think the idea of an exponent representing in sums of powers, right, is more sophisticated and came in later. Okay, another culture brought up on a different base or brought up with, say, the Roman system, right, has, on this view, a different idea of what a natural number is. Now, that might sound rather paradoxical, but it would be a familiar idea of mathematics that some structures may have something in common and can be identified for certain purposes. And here, these are all progressions, all can be used for counting, for giving finite cardinalities, and so on, right? On the other hand, to mention one of the problems I raised then for what Diana Ackerman was saying, it is no longer a surprise that what might be trivial for people brought up one way is non-trivial for people brought up another way. Because it's not just a matter of appearances. They actually have different mathematical concepts corresponding to their numerals. And so, what is a trivial problem in one notation might be very non-trivial in another one. Not because, well, you're simply being asked, what is the answer in this notation, right? That would be something like the Scylla answer. But it's because one is thinking of the natural numbers differently. They are not the same thing for the different cultures. Okay, well, I have some more to say about this, but, this took two separate lectures. They were very long. In order to shorten this one, I archive and knows that there are some other things I have to say about this. There's something that someone said, you must definitely give this example in any version of lectures, but I will leave it out unless asked. I also wanted to give an argument that we should just get as close to making these objects finite sequences of Frege-Russell numbers as would be possible, right? I also want to admit that, of course, and would have something to say about this, of course, a computation in decimal also can be too long, or a number in the decimal can be too long to be taken in. Right? This is actually probably emphasized by Turing, right, in his famous paper on computability, right? And so no system, whatever may be, is going to be surveyable, and we have various shortcuts which will help us, and will help us precisely if we understand the other polynomial representation and things like that. as Mark mentioned. Perhaps, and sorry for the asymmetry, and some significant things are omitted. I mentioned some very peculiar system of notation, which if we thought of that as the structurally revelatory notation, it would satisfy Ackermann's criteria, but would give very peculiar results. Well, I won't say any of these things unless asked. Have some little time, have some mercy on those who have stuck with us. Okay.
Well, thank you very much. Really a tour de force. And I think that we should allow, because I'm sure that certain people have comments to make, and so this is the time. Yes, Professor Posey.
I have 3 questions. First is, or maybe comments. One is whether you seem to take Roman numeral notation and other non-polynomial notations as just as alternatives, just like other base polynomial notations might be alternatives.
Yes.
And I'm wondering whether you might not want to say that. I'm wondering 2 things. One is, it seems to me that in a certain sense, you want to say different polynomial notations on a different basis are structurally revelatory in the sense that the decimal notation might be, while the Roman notation one might want to say is not structurally revelatory.
Yes, well, it's not true.
Because of the they do follow something of the recursive nature of the generation of natural numbers in a way that the Roman notation doesn't. And so there are 2 possibilities there. One is, I'm not sure, one is Scylla and one is Eurydice, but one possibility is that the Roman notation just doesn't get it right. That is that we're being, that there is something about, we've discovered something about the nature of natural numbers in modern set theoretic terminology that the Romans just didn't get right, and as a consequence, we're being too generous to them when we allow that they have, they have a different notion of natural number, perhaps, but it's not as good as ours because we're closer to the way the natural numbers actually are.
Yeah.
That's it seems to me that that's one possibility that one might.
I haven't actually. There's certainly a reason why base notation 1, right? It is not true, though often said, that the invention of 0 was an essential part of this. In fact, we could have, if we had only positive integers, we could represent the numbers from 1 to 10 and include 10 as a single digit. Then 100, for example, would be, instead of 100, it would be 90.
Yes, I know.
Yeah. Okay. I think a lot of people don't know this, so that's interesting. So I have found some people in the audience who usually know this, but one often see that say in print that 0 was an essential part of being able. Now, I ought to think whether there is a proper account that will make the Roman numbers structurally revelatory.
Roman system is based on 8 symbols, and they vary 5-2, 5-2, 5-2. So each symbol is introduced either at the 5th place or at the 2nd place after that, if you go through all the way from I to M.
Yeah. You know, there, of course, are complications in that, you know, for example, yeah, 4 is IV.
It's a different thing.
Yeah, rather than I 4 times and so on. Right. Never.
Just because they were all in the Navy.
Right.
Yeah.
And similarly for 9 and some other things. Nevertheless, I think a structurally revelatory account could be given at the time when Roman numbers were getting replaced by Arabic Hindu numbers. There was actually some controversy over which was the best. It wasn't that the Arabic numbers won immediately. Yeah, I mean, maybe you know that.
Yeah, no, that's quite clear. I don't think that we know, I don't think at that time anyone knew why a base system would be better ontologically. That's what I'm suggesting.
Yes. Well, the Roman system would be more complicated ontologically. It had some calculation advantages, you see, right? By its advocates, like you can add to Roman numerals simply by, well, it's like Chomskyan rewriting system. You put them together, right? Then you have various rewriting rules, like have an X and some I's, you put the X's in front, right? If you are immediate, you know, I don't know, 9 has to be rewritten as IX. There are various rewriting rules, but advocates said that it was actually faster and better in this way, right? Nevertheless, well, thinking of them as structurally revelatory will be a more complicated structure. I think that's true.
Second question is whether you thought of this generalized over higher order objects, which there are also, you know, could be alternative approaches.
Well, look, I mean, I have thought of, look, it's obviously a thing in proof theory. For example, that a structurally revelatory notation for the numbers epsilon 0 is in Jensen's famous proof, right? Should be done in Cantor normal form in powers of omega, right? And there are various other notations that will not be structurally revelatory. I do not know how to define this, and it, of course, is a problem in proof theory, but it also shows that the thing can be extended at least to certain infinite and higher order things, right? Then there are things with higher ordinals and so on.
I'm sure you can thinking about things that where the ordinal structure isn't crucial. I'm thinking of things, you know, in algebra and analysis where alternative notations or alternative bases might have advantages, and whether your idea that there is some privileged one, or that each one gives some sort of ontological basis, might be generalized. And I don't have an answer.
Yeah, I don't know.
You had a third question.
No, that's good. That's good enough.
It's good enough.
Third question,
Okay. Sir.
So, is it necessary to specify a version? Because let's say Frege's version is more intuitive, but for Newman's is more convenient. So can it be just that a number can be anything but must be something? I mean, do we need to specify a version?
I don't think in general we need to specify a version, but of course in practice, Wittgenstein is right that we do, right? And it's not the ones that are usual in set theory. Look, if we actually tried to use the von Neumann numbers, they would be even worse than stroke notation. They would start getting longer and longer because everyone includes all the previous ones, right? So we could not, in fact, use them in a structurally revelatory notation. Our ability to grasp it would fall out very quickly, right? Very, very nice for theoretical purposes, since it extends to a representation of all the ordinals, right, given appropriate assumptions.
Yes, over here.
If I understand correctly, then the motivation for the idea that there is a privilege notation is the intuition that we have that only when an answer has been specified in that notation, only then can we say that we have answered the question, what number is that?
Well,
I first wanted to know if I got
different people may be brought up on different conceptions, right? Right. But given the notation you're brought up on, that will determine the structure of the natural numbers for you. That is the idea. Now, in some cases, the hereditarily finite sets, I thought that notation, well, there are obvious variants of it, but it is privileged across cultures, right, so to speak. I mean, a scrambling of it anyway will not work very well, right?
What I wanted to know was, to what extent are you willing to identify the natural numbers themselves with the objects, say the digits from 0 to 9, and finite sequences of those?
No, so I don't identify the natural numbers with these symbols, right? But with the theory of sequences of such mathematical, finite sequences of such mathematical objects.
The benefit in such an identification would be that it does justice to the intuition that only when you have specified the number in a certain way have you answered the question, what number was that?
Yes. So look, like, if you say, how many marbles in this jar, and it's told 37, then there is no question, what number is that when it's through? See, right.
Now, my question, I have another question.
Okay.
It seems to me that like we have a very similar, if not the same intuition in the case of real numbers. Sometimes you are asked what is the integral of a certain function in a certain interval, and you will accept an answer such as 1 over pi as the final answer.
Yes.
You won't accept anything of, well, someone could just throw the answer back at you and tell you this is the number and give you the expression you gave in your answer, the integral from 0 to 1 of a certain function. Now, for cardinality considerations, it seems obvious that you cannot make a similar identification in the case of reals. So do you have any way of maybe this is repeating Carl's question, do you have any way of extending this approach to the real case, to the case of the real numbers, where, as I said, we seem to have very similar, if not the same, intuitions?
Well, I do agree. And don't have an answer except for their extraordinary place in history. I mean, I think once one tries to extend these things, well, there are certain issues even with rational numbers, right? When one should ask, but what number is that? I mean, if one is given certain decimals like 0.25, right? Then there's still, yes, but what is 0.25? It's a quarter, right? Looks as if this answer is needed, right? Whereas sometimes it might be the other way around. Pi and E and so on, you know. Those particular transcendentals I mean, I can only say, and find this ministers, that they were so basic to our mathematical culture, right? And came up in such natural ways, right? That they are regarded as basic, and more so than if we chose a base other than 10, such as, say, 12, right? It would be a funny group of Martians, indeed, who didn't regard pi and E as basic. Now, obviously, for certain technical purposes, like that we know today, it may even have known a long time ago, such bases as binary and so on might be regarded as, you know, basic too for extracultural reasons, but we do not regard them as the basic thing. I've sometimes been told that there are some people who are so used to binary that they're equally adept. I have not considered the idea of people being equally adept in two representations, right? Then they would have to have two different concepts of natural numbers, according to me, and not know how to translate them. But this is the rare case, if it does really occur, right? Diane Ackerman does mention such a case.
You want to continue? You have a question?
I am willing to continue.
It seems that the Roman numeral system doesn't have that double aspect that you get in the base that I spoke about. So that you could use the same string either to understand as you do some kind of sequence of objects, a finite sequence of objects, structurally revelatory of itself, in other words, of the sequence itself.
Yeah.
Right.
That's what you're revealing, basically. You're revealing. I assume that the reason that these things are buck stoppers in our culture is that they allow the recursive generalization, generation of these objects, but also calculation. I mean, you learn calculation. You can't. When you say something is 35, you also have in mind adding, subtracting, other kind of rules which are made possible by looking at these things as strings. That's how I mean. Whereas the polynomial representation, which you don't really have so much in the Roman case.
Yeah, you don't. Yeah.
Could be.
Or at least
used
not.
First of all, you need to justify these algorithms, which most teachers don't know how to do. You learn them, but you don't justify why is it the right number. Using the polynomial thing at a later stage actually justify why you're doing what you're doing.
Yes, though I actually think, though it's not on top of my head, that without putting things this way, the school rules for addition and so on, right? Could be justified directly without putting things in terms of polynomials, though they are no doubt motivated that way. I mean, look, part of the motivation and also part of our concept of natural numbers is, we can't count a very large set. So even before decimal notation was invented, right? Of course, people thought, all right, let's think of it in groups of 10. We can look at these, right? Then how many groups of 10 are there? And so on. This was part of the verbal system, right? Long before the Indo-Arabic notation was introduced, right? And was also probably, people didn't have the general concept that they were using powers of 10 and coefficients and so on, right?
Yeah.
But they still said verbally, in some languages, things like 534 and so on, right? Yeah, now, in some way, I don't know why that didn't lead to the invention of these systems earlier. Say, in even ancient Hebrew, though some people say that LF really, in some contexts, meant something else rather than 1,000 or whatever, right? But people said things in that way, right? Nevertheless, the Hebrew numerical system, wasn't a decimal system, right? Of course, at least today, I don't know if it's verified that, that they used this in ancient times. Say right rather than just assumed, but you know. Well, you know, it's certainly not a positional system either, right? Right. So, yet, you see, our verbal system might have suggested to people, right? And if they got the idea of a polynomial representation, that such a system should be used. But it didn't to most cultures for a long time, as far as I know. Right?
If I think that, did you want to say something?
No, I thought maybe.
I think so too.
Point and then
I think that I want to thank you all for sticking this out. I think it was a fascinating presentation, and we were well rewarded with the second lecture, so thank you. And I wish you all a very good evening. Thank you.